And today we are starting chapter 12. We're going to learn some basic statistics in chapter 12. We are going to start with population and sample. It is a pair of definitions, very important and basic. Let me gonna start a new page. Population is the set of all the subjects in discussion. Depends on what you concern in your research. Let's look at the example. You want to do a research, you want to study, you want to know the average height of all the adults in the United States, right? So let's say your research is want to know the average height of all, how about male adults in the United States. Okay, then the population, your population would be all the male adults in the United States. So those people, those male adults make a set. That set is the population. Population includes all the subjects in discussion, under consideration. And a sample here is a subset of the population. Sample does not include all the subjects in the discussion. Is only part of the population. So sample here is just a subset of the population. Let's go back to your research. The goal of your research is to want to know the average height of all male adults in the United States. Ideally, what you're gonna do is you measure every single one of them, right? Yeah. I'm not sure the exact number of male adults in the United States, but I know that is a very large number. So if you measure each single of them, it's gonna take forever and very not practical, right? So when go through every single subject in the population is time consuming, energy consuming, sometimes unnecessary or not practical, we consider to get a sample. We consider to take a sample from the population. And of course, we hope the sample is representative. The average height from the sample could be a good estimation of the average height of all the male adults in the United States. Okay, so when the population is very large, it's not practical or unnecessary to go through each single subject in the population. We get a sample. Sample is a subset of the population. It is a part of the population. So maybe you decide how do you get your sample. Maybe you would consider randomly pick 1,000 people from each state, right? And we have 50 states. 1,000 people times 50, that is 50,000. and that is your sample, right? So the way you get your sample is actually stratified sampling method, but we don't have to know that at this point. What you have done, what you do is the country has 50 states, right? From each state, you randomly select 1,000 male adults. So in total, you would have a sample of size 50,000. You would have 50,000 subjects in your sample. And of course, we hope their heights represent the height, the average height. Their average heights represent the average height of the population, right? So you will not purposely only pick basketball players and to be part of your sample. You see what I'm talking about? If you only pick the athletes, especially playing basketball, those people are pretty tall, taller, probably a lot taller than the average males, right? So if you do that, you would end up with a biased sample. For sample, biased sample, representative. We want a sample representative. We don't like biased sample, right? So that's the reason when you take your sample, you want to randomly select 1,000 people from the state, from each state. And we have 50 states, so you end up with a sample containing 50,000 subjects. Suppose measuring those 50,000 male adults is doable. So you have their measurements, right? Let's say the first subject, the height is x1 and x2, all the way to x sub 50,000. So those are the measurements of those 50,000 male adults in the sample. And then you're going to add them together and then divide by the sample size, which is 50,000. And you will have an average. You would have an average height. That average height is the average of the heights of the 50,000 subjects in your sample, and we call that sample mean. We call this sample mean. In reality, in real world, we call average, but in statistics, we use a more professional terminology, which is mean. Mean means average, okay? Since the mean is the average heights of the subjects in the sample, it is called the sample mean. X bar is a notation to denote sample mean, okay? Okay, so if the sample is representative, then we can see X bar, the sample mean, as a good estimation of the average height of all male adults in the United States. We call the average height of all male adults in the United States in the population mean. So here we have a unique notation for population mean. We use mu. It's called a mu. It's not m. It has a longer leg, right? It's a mu. We call mu the population mean. The idea, so the goal of your research is to know what's the population mean, right? The average height of all the male adults in the United States. The average height of the population. But it is not practical or not necessary, so we decide to take a sample. We get a random sample by randomly select 1,000 adults, male adults from each state, and then we will have a sample with 50,000 male adults, and then we measure those people, and we get an average height, and that average height X bar is called the sample mean. Under the condition that the sample is representative, we could use the sample mean to be a good estimation of the population mean. Okay, does that sound make any sense? If you are the researcher, when it's not necessary or not, it's not doable to measure each single of the male adult in the United States, in the country, you would consider to get a sample, right? Probably your sample is a lot smaller than what I had here, because 50,000 is also very, very large. But compare with the population is a lot smaller, right? Okay, so here, am I clear about what is a sample and what is a population? Population is the set containing all the objects that in a consideration depends on your research. Sample is just a part of the population. Sample is a subset of the population. Some samples are good, some samples are bad. If the sample is representative, then it's a good sample. If the sample is biased, then it's not a good sample. Earlier I mentioned you want to know the average height of all male adults in the United States. But if you purposely, pick the basketball players to measure, of course the average you get, the sample mean you get is overestimate the population mean, right? So that is going to be biased. All right, another set of definition closely related to population and sample is a parameter and a statistic. By the way, statistic here is a singular. Singular. Give you an example. Apple, singular, right? Apples, plural. Okay, so statistic is a singular. What is parameter? What is statistic? It's pretty straightforward concepts. A statistic is a numerical description of a sample. I can actually write it down I can actually write it down here. Thank you, Ashley. Statistic or a statistic is a numerical description of a sample. So statistic corresponds to sample. A parameter is a numerical description of a population. So parameter corresponds to population. In our example, population mean is a parameter. It describes the average of the population. Okay, population mean here is a parameter because it describes an average, the average of the population or the center of the population. And the sample mean, X bar, sample mean describes the center or the average of the sample. So X bar here, the sample mean is a statistic. Very straightforward, right? Yeah, of course we have other parameters and statistics later when we go to section 12.2 and 12.3. Right here we have those two. Population mean corresponds to population, describes the population, so parameter. Sample mean, the average of the sample, so of course that is a statistic. And chapter 12 talks about statistics. All right, this word has two meanings. It could be a mathematical branch, like we are studying this chapter, we are studying statistics. Okay, a mathematical branch. Or it could also be the plural. It could also be the plural of statistic. Right? We just learned what is a statistic. A statistic is a numerical description of a sample, corresponds to a sample. Well, if we have more than one statistic, then we have multiple statistics. But that is just the plural of this word. It's different from the, we're studying statistics. I hope you know what I'm talking about here. Just something that you want to know because you are learning statistics this chapter, right? All right, so let's go back the guided note. Let's look at some other information. I want to share this example about taking a sample. I mentioned sample could be good, sample could be bad, right? Of course, we do not want a bad sample. We do not want a biased sample. So we're going to be careful when we select the sampling method. Let's take a look at this example. A group of hotel owners in a large city decided to conduct a survey among citizens of the city to discover the opinions about the casino gambling. That's the research. Part A, describe the population. I ask a question. Sometimes I really hope you can answer, but sometimes, more times actually, I just want to encourage you to think. Think about this one. A group of hotel owners, so those are the researchers. They have certain interests, okay? In a large city, decide to conduct a survey. What's the purpose of a survey? And who they are going to survey? They want to survey citizens of the big city. So citizens of the city, right? To discover their opinions about the casino gambling. So the purpose of the survey is they want to know how citizens of the city think about casino gambling. Maybe they would, if a lot of people show their interest in casino gambling, maybe those hotel owners would build some casinos in their hotels. It's just, something like that. What's the population here? Population is a set containing all the subjects or objects in discussion. So here is obviously the population is all the citizens of the city. Okay? Let me know if you do not agree. Part B, one of the hotel owners suggests obtaining a sample. Obviously, the city is very large and very difficult to get all the opinions, right? So they decide to obtain a sample. How do they get a sample? By surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Okay. Actually, doing the sample is very difficult, okay, in reality. Especially when your subjects are human beings. It's very, very complicated. It also involves legal issues. So one owner suggests to get a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? This is to ask if you get a sample from the people hung out at one of the 6 of the largest nightclubs on a Saturday night. Do you think that sample is representative or that sample is biased? Would that be a good sample or a biased sample? This I need you to answer. What do you think about this? biased for sure, right? Yeah, for sure. Those people who hung out in the large nightclubs on Saturday night, they have their own personalities, right? Very outgoing. They probably, it's really hard to say. They probably want a casino. Then they can hang out in a casino, right? But what about other people living in the city? Like people like me, I don't go out at night, right? So that definitely this is not a representative sample, not a representative sample, it's a biased sample. If the owners make decisions on a biased sample, they might end up with a failure. Okay, they might end up with a failure. Okay, so let's go back. Ideally, we want to use a small sample to make decisions, and we can make a generalization about the larger population, right? But the sample has to be representative. We want at least the sample is a random sample. So here we have the definition for a random sample. A random sample is a sample obtained in such a way that every element in the population has an equal chance of being selected for the sample. At least it has to be random sample. The sample in part B of the example we were talking about is not a random sample. If they only go to the nightclubs on Saturday night, other people who do not go out at night or do not go out on Saturday or never go to nightclubs, those people have no chance to be taken. So definitely not a random sample. To guarantee a random sample, the method has to make sure each single element in the population has the same chance to be taken. Okay, let's look at this example. We return to the hotel owners in a large city who are interested in how the city's citizens feel about casino gambling. Which of the following would be the most appropriate way to select a random sample? Well, obviously, that owner, the suggestion is not a good idea, right? Then what is a good idea? What is a good idea? How could they get a representative sample, a random sample? Part A, randomly survey people who live in the oceanfront condos in the city. I don't think that would give you a random sample, right? Obviously, who can afford to, live in the oceanfront condos? Rich people, right? So biased for sure. B, survey the first 200 people whose names appear in the city's telephone dictionary. This one's a little bit tricky. Maybe you feel like, oh, that's not a bad idea, but in fact, it's a bad idea. This sampling method is a convenient sampling method. In general, a convenient sampling method will result in a biased sample. To get a random sample, it takes effort. And this one is easy, very convenient, right? Okay, just let me look at the yellow book. Of course, you guys don't probably never see a yellow book like years ago. And the telephone book dictionary only pick the first 200 people. That is very convenient. That definitely is not a good idea, okay? It's convenient sampling method, and in general, a convenient sampling method results in a biased sample. Part C, randomly select the neighborhoods of the city and then randomly survey people within the selected neighborhoods. That sounds okay, right? Yeah. Randomly select the neighborhoods of the city and then randomly survey people within the selected neighborhoods. Yeah. Compare with the other two, part C is a bad idea. But actually doing this is very troublesome. Imagine you are assigned that task. You have to go to all the neighborhoods. You have to randomly select the people to survey, right? That's a lot of work. To get a random sample is not that easy. All right, let's keep going. Okay, so one definition in the guided note is incorrect. It said the data has to be numerical, not necessary. Okay, data could be qualitative, does not have to be quantitative. Yeah. So this book, that part is a mistake. It could be numbers or you know, like your opinion, right? Your opinion also is data. You know, your gender is also data. Your personality, your habits, your routines, those are all data. Data do not have to be numerical. It could be non-numerical. Just to let you know. So consider, obviously, we just want to consider numerical data. Consider we got a sample and a bunch of numbers here. Suppose, for example, researchers are interested in determining the age at which adolescent, like teenager males, show the greatest rate of physical growth. A random sample of 35 10-year-old boys is measured for height and then remeasured each year until they reach 18 years. The age of maximum yearly growth. Okay, this is what the sample data is representing. Okay. We get a bunch of numbers. What are the numbers even mean? 35 numbers from 35 teenagers. And those numbers represent the age, their age of maximum yearly growth. Okay, for example, the first 12 means that subject, that boy, grow the maximum height when he was 12-year old. And this data, this value, represent the second subject. That boy had the maximum height growth when he was 14-year-old. So that's how do we understand the values. It's not just a bunch of numbers, it has meanings. All right, so that's the sample. A piece of data is also called data item. I sometimes say data value. This list of data has 35 data items. Some of the data items are identical. 2 of the data items are 11. Thus, we can say that the data value 11 occurs twice, or 2 boys who have the maximum height growth when they were 11 years old. Similarly, because 5 of the data items are 12, the data value 12 occurs 5 times. We call that frequency, okay? We call 5 as the frequency of the data item 12. Since there are 5 boys who had the maximum yearly growth in height when they were 12 years old. So we have 5 12s in the data set, in the sample. And we say, since 12 appears 5 times, we say 5 as the frequency. Okay, 5 is the frequency of the data item 12. Okay. Collected data can be presented using a frequency distribution table. Okay. So once you have the sample ready, you want to analyze and you want to see what you can get from the sample, right? So you have to analyze, organize, analyze the data. How do you do that? A frequency distribution table is a good tool. A frequency distribution table is a good tool to organize and analyze a sample. In this case, we have a sample of size 35. Those are 35 numbers. And some of them are, some of the values are identical, right? So we want to see the frequency for each value. The smallest number is 10. How many tens in the sample? How many tens in the sample? And this is, I believe everybody can do that. It's just a little bit time consuming. I take a glance, I only see 110, so the frequency of the data value is 1. Data item is 1. And 11, how many 11s do we have? I take a glance, and I notice 11 appears twice. So 2 is the frequency of the data item 11. And 12, how many times 12s appear? It says appear 5 times, right? You can double check, but I believe it's 5 times. So the frequency of 12 is 5. And then 13. How many 13s do we have in the sample? We have 1 here. You can do this, okay? This is 13, this 13, this 13, this 13, this 13, this also 13, this 13. A lot of 13s, right? And you count it. How many of them? 1, 2, 3, 4, 5, 6, 7, right? 7 of them are identical, equal to 13. So 7 is the frequency. 7 is the frequency of 13. And then keep going. Yeah, we can erase those, or we can keep them. And now let's see 14. 14 appears once, twice, 3, 4, 5, 6, 7, 8, 9. If I didn't see them, please let me know. So what I see is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 14s. So the frequency for 14 is 9. 15. And erase those. Let's see how many 15s are in the sample. 15s here. 1, 2, 3, 4, 5, 6. 6 of them, right? If I made a mistake, please let me know. How many of them? 1, 2, 3, 4, 5, 6. 6 is the frequency of data item 15. Now do 16. Pretty interesting, right? Yeah, I was just kidding. I know it's very tedious. 15. Hold on, huh? What are we gonna do now? 16? Yeah, 16. So 16. 1, 2, 3. Oh, the frequency of 16 is 3. It's 3. 17. Let's see how many 17 do we have. 17. 1. Just one. Just 117. Yeah, that boy had the greatest growth in height when he was 17. It's pretty late. Consider most of the boys, have the highest growth around 14, right? So 1. The frequency of 17 is 1. The last one, 18. How many 18 do we have? 1. Just 1. Also 18 is 1. Frequency for 18 is 1. Okay, so this table is called the frequency distribution table for the data set, for the sample. The first column, frequency distribution table always have 2 columns. The first column is all the possible values in the sample. And the second column has the frequencies for those data items. You should understand it, right? Yeah. Obviously, for this example, there, majority. So how do you interpret the result? So majority of the boys, they have the biggest growth in height between 12 to 15 years old, right? Yeah, and only a few people, there's only one boy had the biggest growth at 10-year-old, is very early, and only one at 17-year-old, the other one is 18 years old. So you can see, you can draw some meaningful conclusion based on the frequency distribution table. Does that make any sense? And you can compare if your son, suppose you had a son, if your son, the growth, the highest growth occurred in 17 years old, you can say, okay, that is actually minority, right? But if your son had the biggest maximum growth in height when he was 9-year-old, okay, this boy is very normal, right? Very normal, like most of the people. So you can make a meaningful conclusion. Does that make sense, everybody? And knowing the frequencies in the second column, in the column of frequency, must add up to the sample size. You can try, add those numbers together, you would have 35. That's the sample size. Sample size is the number of data items in a sample. Okay, we call that sample size. Normally, we use little n, little n, lowercase n to represent the sample size. So far, so good, everybody? Yeah, this section has a lot of small things. Not like one topic, I can just start to do problems. A lot of small things, small concepts. Okay, very good. All right, very good. Now let's look at this problem. A frequency distribution table that lists all possible data items can be quite cumbersome when there are many such items, right? Yeah. And earlier, the sample size is only 35, is pretty small. But what if you have a lot items and you finding the frequency for each is very troublesome? And we actually do what? We can do what? We can find the grouped frequency distribution table. This is another very powerful tool in statistics that we can use to analyze and to organize and analyze samples. So this is another tool. It's called a grouped frequency distribution table. We use a grouped frequency distribution table when the sample size is quite large, and make this type of frequency distribution table inefficient. So we're gonna try to use a grouped frequency distribution table. How do we do that? Normally, so this is a little bit subjective, okay? The grouped frequency distribution table you create might be different from mine. So it really depends on how do you want to classify those data items, okay? And it also is related to the research purpose. So what are we gonna do? What are we gonna do is find the minimum and the maximum in a data set, in a sample. We're gonna find the minimum and the maximum. Let's see which value is the smallest. Which value is the smallest? Which value is the smallest? Is 43 the smallest number? Let me just take a quick look. 43, 45, 40, yeah, I think so, yeah. So 43 is the minimum, and what's the maximum? Minimum is 43. And what's the maximum? 90, I saw 94. Do we have a number bigger than 94? Guys, is 94 the maximum? Help me to look. Yeah, very good. Thank you. Yeah, let me just look at it again. So we have 94 here. That's 92. 94 here. That's 94. Yeah, 94 is the biggest, is the largest. So from minimum and maximum, we want to find some convenient whole numbers. 43 is not a convenient number. 94 is not considered a convenient number either. So one way to classify or group those values is doing this. Okay, is doing this. This is the classes. This is the classes. Remember, minimum is 43. Maximum is 94, right? So start from 40 is a good idea. 40 is close to 43 and also convenient, right? 40 is more convenient than 43. So start with 40 is a good idea. And end with 99 is also fine, right? So we decide to use the class width of 10. Okay, class width of 10. And we are going to use 40 to 49 as the first class. 50 to 59 second class. 60 to 69 class 3. 70 to 79 class 4. 80 to 89 class 5. 90 to 99 class 6. So how many classes do we have here? 1, 2, 3, 1, 2, 3, 6 classes. Means we are going to divide, the numbers, the values in the sample, in the data set, into 6 classes. And then we need to make sure the 6 classes contain or cover all the values in the sample. Okay, it seems does, because the first class start with 40, ends at 49. The second class start with 50, ends with 59. There's no gap between 49 and 50 because our data values are all whole numbers, not decimals. So we won't lose any values between the classes. So we are fine, all right? And how do we create the grouped frequency distribution table once we have the classes determined? I think this is a very smart way to group the values, right? Of course, you can make your own. Yeah, maybe you want to do 40 to 44, right? And then 45 to 49. You want more classes, but normally we want to have 5 to 20, this many classes. Depends on your research. And this sample isn't that big, so 6 classes sounds very nice. And then we're gonna do the tally again. So basically, give me 1 second. Let me copy paste the data set right above. Copy. I'm gonna do copy. Paste. That's the data set. That's the data set. All right, that's the data set. We wanna create the grouped frequency distribution table for that sample, for that data set. So tally means what I just did earlier. So we want to know how many values in a sample fall between 40 to 49. what you can do. You ready? Okay, very interesting, right? Okay, am I missing any? Let's see. Okay, from 82. Okay. So let's see how many of them fall between 40 and 49. I'm gonna go by column. The reason I do by column because we have less numbers in a column and more numbers in a row. So to be more efficient, I'm gonna do column. First column, any number between 40 to 49? No. Second column, this one, between 40 to 49. And that's it. Next column, between 40 to 49, none of them. Next column, between 40 to 49, no. And this one, between 40 to 49, no. This one, we have 1, right? Between 40 to 49. This one between 40 to 49. Inclusive means if it's 40, of course, we won't have 40 because the minimum is 43. But if we have 49, we include that, right? And the last column, between 40 and 49, between 40 and 49. Okay, that's it. So we have 1, 2, 3. 3 data items in the first class. So the frequency of the first class is 3. All right. And the next class is from 50 to 59, inclusive. If we see 50, we're going to count it. If we see 59, we're going to count it. All right. Yeah, from 50 to 59. Let's see how many of them are between 50 and 59. The first column, 50 to 59, this one. Second column, 50 to 59, nothing. This one, 50 to 59, this one. This column, 50 to 59, this one, basically 50 each, right? As you can see, it's convenient this way to classify the values. Next one, 50 to 59. Next one, 50 to 59. 50 to 59, the last column, right? So count the number of the black lines I just have. 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6. 6 of them. So the frequency of the second class is 6. Do you see the idea, everybody? I don't think it's necessary to complete the whole table, but we should get an idea already how to complete the table, right? Right? Yeah, I'm not going to do that because it's very time consuming. The purpose is we know how. Yeah, exactly. Thank you. So we're going to skip that, all right? And I think we might have the result later. Let me see. Do we have that? Oops, we don't. Hold on. Oh, we don't. All right. Yeah, let's say we have the table complete, and that table get rid of the middle column, because same with the frequency distribution table, grouped frequency distribution table also only has 2 columns. First column classes, second column frequencies, and the same thing. Those frequencies in the second column should add up to the sample size, which is the total number of the values in the sample. Okay, and we have some other concepts to understand. Pretty important. You might see them in the exam, so we need to learn those concepts. For each class, the first number is called the lower class limit. The second number is called the upper class limit. So the lower class limit of the second class is 50. The upper class limit of the second class is 59. So you can see those numbers, those blue numbers, they are lower class limits. And those yellow numbers, they are upper class limits. Okay? And we also want to know what is the class width. This is the most important a thing about a frequency distribution table for some reason. Okay, you need to firstly remember the name, class width of a grouped frequency distribution table. Let me type the definition here, okay, then you can write on your notes. What is the class width? The class width of a grouped frequency distribution table is the distance between any two consecutive lower limits. Okay, yeah, firstly, please write it down, and then we look at the table. You might realize the definition of the class width is different from what you thought. You might realize, oh, that is the class width. It's different from my thought. Okay, make sure you write it down. The class width is the distance between any two consecutive lower limits. All right? Very important. Pretty much sure that you're going to have that in the exam. The class width of a grouped frequency distribution table is the distance between any two consecutive lower limits. All right, let's go back to the table. Pick any two consecutive lower limits. The distance between them is 10. As you can see, from 40 to 50, 10. From 50 to 60, 10. From 60 to 70, 10. So the distance between any two consecutive lower limits is 10. And actually, the distance between any two consecutive upper limits is also 10. So we can also define class width as the distance between any two consecutive upper limits. Same thing, right? So the class width is 10. The class width is 10 in this case. It is not 9. A common mistake, consider, okay, class width. Okay, maybe it means the length, means the width of a class. And the first class from 40 to 49, the width is 9. No, okay? That is the range. That is the range of the first class and the other classes. That is the range. Upper limit minus lower limit, that is the range. That's the range of the first class, also the range of other classes. So it's different from class width. Mathematicians decide what is defined as the class width. Okay, we have to follow that. Again, class width is the distance between any two consecutive lower limits or consecutive upper limits. In this case, 10, not 9. Am I clear, everybody? Okay, you might encounter, okay, very good, thank you. You might encounter a problem in the exam. Just ask you, give you a frequency, group the frequency distribution table. What's the class width? Please do not mess it up. It's supposed to be an easy one. Okay, let's go back. Tables, frequency tables are just one tool to organize and analyze a data set. And we also have other types of tools, for example, graphs. All right. So next, we are going to look at the frequency distribution histogram. Okay, let's look at what is a histogram. You might or might not heard of this word, but it is a very important type of graphs in statistics. It's called a histogram. This graph is a histogram. It is not a bar graph. So I need to point that out. It is not a bar graph. Yes, it has bars, but it is not a bar graph. The main difference between a histogram and a bar graph is the bar graph has gaps between bars. Histogram, those bars touch each other, no gaps, okay? That's the main difference. Also, histogram is for quantitative data, like numerical data. And the bar graphs mainly is for qualitative. Yeah, I need to learn how to pronounce that better. Qualitative data. Okay, so bar graph is for non-numerical, histogram is for numerical. So it's different. It's different. Even histogram has bars. So as you can see in histograms, in a histogram graph, you have multiple bars, right?
I said I enjoy him coming down because they're fun and talkative and they just say all kinds of things. And it's right. And I know you have fun with Get off the steps. And I love when they come down and show their new dresses and they'll go come down.
Okay. I'm not sure how do you learn well by multitasking. So histogram has bars. Those bars have the same width. You know, interesting thing is those bars has equal width, right? This is the width. This is the width. And this is the width, right? They have the same width, but they have different heights because their heights represent the frequencies. So this is a frequency distribution histogram. This is a frequency distribution histogram. This histogram corresponds to this frequency distribution table. We are familiar with this table, right? We actually completed that table. Remember, 35 teenagers, and we collected their age when they had the maximum growth in their heights, right? So yeah, remember this table? And this histogram corresponds to the table, okay, corresponds to the table. So it provides a better visual effect. You can see the distribution better. Yeah, you can see the distribution better. On a horizontal scale, we have all the values in the data set, 10, 11, all the way to 18, right? So we have this many bars. Yeah, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 values in the first column. So we have 9 bars in the histogram. And the height, they all have the equal width, by the way. And their height of the bar are the frequency. For example, the frequency of 10 is 1, right? So the height of the first bar is 1, as you can see. The frequency of the second value of 11 is 2. So the bar at 11 has a height 2. The frequency of number 14 is 9. So the bar at 14 has a height 9. And with the graph, you can really see the frequency very clearly, right? Very clearly. Do you guys have any questions? Do you see the correspondence between this frequency distribution table and this frequency distribution histogram? Okay, thank you. Thank you, Jack. I think I understanding. Okay, perfect. Thank you, Ashley. Yeah. It's just a lot of small things, but they are not very difficult to understand. Let's continue. Besides frequency distribution table, frequency distribution histogram, sometimes we use frequency polygon. Polygon is just, look at this graph on the left. It is a closed shape, figure. And they take for example, the number they take the points with the x coordinate as the value of the data, the second coordinate as the frequency of the data, right? So 10, 1 means the first value in the data set is 10, whose frequency is 1. So 10, 1. And this point is 11, 2. 11, 2 means we have two 11s. Well, the frequency for the data item 11 is 2. And this one is 12, 5, because the frequency of 12 is 5. So the height is 5. So we have those points found and we connect them. Very important thing is it close here. I'm going to stress it close on the x-axis. It doesn't stop here. It continue and close on the x-axis. So it make a enclosed figure like that. All right. So that is a polygon. I don't really use polygon that much because, you know, histogram is already very good enough. Okay, so next plot we are going to introduce is called a stem and leaf plot. As the name shows, this type of plot has two parts. Part 1, the stem. Part 2, the leaf. We are going to use the data showing statistics test scores for the 40 students to construct a stem and leaf plot. Okay, so we are going to look at this example and figure out what is the stem leaf graph, stem leaf plot, and how do we create it. All right, so this is 43. Remember the grouped frequency distribution table? We had that. Since those values in the sample, they are 2-digit numbers because they are scores, right? Yeah, they are scores. The minimum score is 43, the maximum score is 94. So the stem is going to be the tens. The leaf, so this is stem, and the leaf is going to be the ones of the number. Okay, each data item has 2 digits in it, right? The first digit is tens, so that's the stem. The second digit is the ones, that's gonna be the leaf. We always do the ascending order, okay? Most of the time, ascending order. So ideally, you have those 40 values sorted in the ascending order and have the minimum like 43 the first, right? Yeah, that's ideal. Ideal is that. And you can get that done by using, by the way, by using TID for calculator. Yeah, if you are interested in that, you can do that later. And we are not going to do that because I do not have the values in the calculator ready. But let's see. So if we go to stat, edit, you can see we have a lot of lists, right? You should have 6 of them. I'm gonna clear some of them. Yeah, this is from my previous work. And this list have how many values? 10 values. I'm gonna show you how do you sort those data, okay? How do you sort those data? Right now, they are not in order. They are not in ascending order or descending order. Yeah, how do we make them have the order? So we can try stats. You see that? Sort, ascending. Sort A. A means ascending. Sort D. D means decreasing, descending. So if you want ascending, we do the number 2. We do number 2. L1. So second one, that's list L1, right? Then let's go back. Let's see if it's there. If not, we'll figure it out. Hold on. Oh, okay. How about we do this? We highlight L1, L2, And then we go to stat sort L1, second one. And then we go to stat edit. It doesn't work. Yeah, how do I do that before? Oh, it's already did. Oh my gosh. It's already did. Do you see that? It's already sorted. Do you see the numbers actually right now is in ascending order? It wasn't in the ascending order. Okay? Yeah, when you see DONE done, it's actually already did it. So normally I would copy, for example, I go to L2 and copy L1 in L2 just to make a copy. And then I sort the one of them. Now I have the original and the new. Do you see what I'm talking about here? Am I confusing or not? It's just use the ascending order, the function. You can do that. Okay, perfect. Really good. So I'm just saying, if you take time to enter those 40 values in the TID4 calculator, and then you put them in ascending order, that will be helpful to create its corresponding stem and leaf plot. Well, now we don't have the ascending order, but let's try, okay? So the smallest value is 43, all right? So the stem is 4, the leaf is 3, and then second least, besides 43, what do we have? How many 45 do we have? Yeah, really, if we have this in the ascending order, that would be very helpful. So 43 is the smallest, and then we don't have 44, right? Do not see 44, but we see 45. And I see 145, so put a 5 here. And then we have 46. 46. Take a glance. 46. We do not have a 46. So do we have 47? We have 147. 47. Since we have 147, so we're going to put a 7 here. Do we have a 48? Do we have 48? 48. We do not have 48. Do we have 49? 49. We do not have 49. So that's it. That's the first step. This shows in the data set, we have a 143, we have 145, we have 147. And then we do 50. Okay? Do we have 50? We do. We have 1. How many 50s? That is 1. Just 1, right? Okay. Then just put a 0 here. Do we have 51? 51. We do not have 51. We have 52, 52. 52. We do not have 52. Do we have 53? I don't see it. But do we have 54? We have a 54 here. Do we only have a 154? Seems like that. Do we have 55? 55. I do not see it. Do we have 56? We have 56 here. 56. We have 156. We have 57. I think I see it. 157 here. 57. 2. Okay. Now I got a 257. Then what should we do? Yeah, look at, do we have any other 57s? Turns out we have two 57s. Then just write 7 twice here, okay? Write 7 twice, very important. Means we have two 57s. Do we have 58? 58. No. Do we have 59? Yes. How many 59? Just that one. And that's it. So that's the second stem, okay? That means when you look at the stem leaf graph, you can tell in the data set you have a 150, 154, 156, 257s, 257s, and a 159. All right? Yeah, again, if we have time to enter the 40 values in TI-84 calculator and then sort it in ascending order, and that will be very helpful when we create the leaf graph. But I believe I'm pretty clear about how to construct this type of graphs, right? Am I clear? And what is this type of graph? Just two parts, stem and leaf, right? Do you have any questions? Okay, very good. Thank you. Thank you for your response. All right. So let's see. Okay, very good. Thank you, Crystal. I think I understand this section pretty well. Yeah, it's not very deep, but very useful. It's very good content, very good section. And advantage, let's see what is this about. Okay. All right. So the next topic of this section is about deceptive graphs. In reality, from the news, from magazines, from the media, we see graphs all the time. But sometimes the graphs are misleading. Okay, so we want to be able to see, oh, that graph is misleading. We want to be able to see it. It's deceptive. So the last topic of this section is about the deceptive graphs. Okay, so the problem is not that statistics lie, but rather that liars use statistics. Graphs can be used to distort the underlying data, making it difficult for the viewer to learn the truth. One possible source of misunderstanding is the scale on the vertical axis used to draw the graph. For example, this one. This graph on the left and this graph on the right, they both correspond to the table in the middle. Let's see, what does the table say? The table gave a few years from 2015 to 2019 and the poverty rates for those years. The poverty rate for 2015 is 13.5%. Poverty for 2016, 12.7%. For 2017, 12.3%. 2018 is 11.8%. 2019 is 10.5%. The trend is very obvious, right? It's decreasing, descending trend, decreasing trend. But the graph on the left compare with the graph on the right, and you can see the graph on the left emphasize the decreased amount, but the graph on the right kind of like temper the decreasing effect, make it like a very mild, right? And what's the difference? What's the difference? Why is it like that? As you can see, the graph on the left is not starting with 0%. Okay, it basically starts from 10.5%. So it stretched, vertically stretched the graph. And the graph on the right, as you can see, also the scale is bigger, like a kind of like a compressed, like make the vertically only make the graph shows this much, right? So kind of like a compressed. It starts from 6% and 8%, 10%. So each scale represents 2%, 2% each scale. But here, each scale is 0.5%. Yeah, so the graph on the left stretched the vertical scale. And the graph on the right kind of like shrunk because it's 2% for each scale. So if you are, so let's say two people, A is the current officer or president in the office, and B is the one won the challenge candidate. Okay, they both gonna compete for the office, right? So the current president would want to use this graph to show, look what I have done. When I was in office, the poverty rate has gone down so much, right? But the other person would want to use this one. Oh yeah, a little bit, right? So something like that. So be aware when you see a graph in the media, do not just believe it. Even right now, the news, I cannot watch the news anymore because it's so depends on which party. They don't even respect the fact anymore. So be critical. Be a critical thinker. And that's pretty much everything for today. I'll see the essential class in 10 minutes, and the other section I'll see you on Monday. Yeah, we're gonna do some practice in Pearson later. Okay, see you in 10. Bye. Crystal, no worry about that. I'll fix your attendance. Thank you. Bye bye.